This oscilloscope is for use with the Arduino Mega and operates with a 20 MHz TLC 5510A analog to digital converter. I'll just connect the port from the Arduino. The timescale for 1000 voltage values is 0.051 milliseconds. The trig point's very stable. I'll drop it back to 5 MHz just to get a few more waves on the screen. I can increase the triggering, decrease the triggering, I can invert the triggering. In this case I'm using level triggering. I've also got an option to do edge triggering for square wave applications. A note on the basic principles. Bob Davis did some excellent work on realizing that an analog to digital converter running at a very high rate could produce data at a faster rate than the Arduino could read. His elegant simple solution was to pass the data to a FIFO that could keep up. Now if you clock both devices at the same frequency, then it will capture data at the same rate as it's being obtained by the analog to digital converter. Once the FIFO is full, it flags and the Arduino knows that the data is ready. I use a 2K FIFO, so I'm passing 2K of information through to the Mega. Once the Mega has that, in memory it can search precisely for the trigger point. Once it has that trigger point, it then says, I'm going to now send from this point onwards 1000 bytes of information to the PC. This of course makes the trigger point very reliable. Put it back onto positive triggering. I can demonstrate that I've got live data here. I can alter the frequency of my source. I can alter the amplitude of my source. The input range I'm using here is buffered with a voltage follower, a high frequency voltage follower. The input is put across 4 laddered resistors, matched values. At the moment I'm off the top of the ladder here, so I've got 4 volts maximum coming in. The reference on the analog to digital converter is 4 volts. Should I wish to go higher than that, then all I got to do is drop down my ladder. I've got 4 equal resistors, so if I go 3/4 of the way down my ladder, I now have a 0 to 5.33 volt device. I'm just going to drop the trigger in anticipation now of going halfway down my ladder. I've now got a 0 to 8 volt device. A quarter way down my ladder, I've got a 0 to 16 volt device. I'll come back up to using the full voltage. Now because I've got information going into a computer, I may as well make use of it. If I pause my capture, I can ask the computer to do some work. I've got here about a 10.9 kilohertz source wave. It's got an average of 2.34 volts. It's got a root mean square voltage of 1.04. Should I want to, I can save the graph. Should I want to, I can save the data. The possibilities for analysis are limitless once you have them in a computer. I also have an AC input setup, which I'll now show you. If I switch to AC and unpause, I'm going to switch the triggering off to allow it to come through. I've got a 2.2 microfarad tantalum capacitor in the line. I've got a simple potentiometer. After that, I can alter the value of the potentiometer so that I can offset my Y to wherever I want on the screen, essentially. If I now get that roughly in the middle and apply a voltage across it, and reapply my triggering, I've got an AC coupled system. And that's it.